Bismillah Rahman Rahim. Calculate V naught in the circuit shown in figure 1. So this is figure 1 and this is the circuit given. Uh, this circuit has two sources, this voltage source here and this current source here. The particular thing about this circuit is that the voltage source is operating at different frequency than the current source. The frequency of the voltage source is 5 radians per second and the frequency of this current source is 10 radians per second. So we cannot transform this circuit, entire circuit completely using both the sources in the phasor domain simultaneously. So what we'll have to do is we need to turn off one source first and then find the response due to the remaining source and then perform the same process again, that is turn off the first source, the earlier source, and then find the response due to the other source and then add the responses together. So that is basically superposition. We will have to use a superposition to find the response for this circuit. So let's first turn off this current source here. Turn off current source. So when we turn off current source, we actually open the source, that is open the source. And when we turn off a voltage source, we basically short circuit the source, right? So turning off the current source, the remaining circuit with only one source is redrawn here. So this is 0.2 farad, this is 1 Henry, this is 8 ohm, and this is 30 sine 5t volts, right? So let's call this fig 2. So we need to transform this circuit, obtained circuit from the time domain into the phasor domain using the frequency of this voltage source here. So omega here is 5 radians per second and the source voltage source 30 sine 5t, it needs to be transformed into the phasor domain. So we could first transform the sine function to the cosine function and then find the phasor, or we can even use the sine as the base. uh, so 30 angle 0 degrees volts, but when we obtain a result in the phasor domain and then transform it back to the sine, to the time domain, again we will have to use the sine function then. So this is the voltage source, then 0.2 farad capacitor, that is 1 over j omega c in the phasor domain, that is minus j over omega is 5 and this is 0.2. So 5 into 2 is 0.2 is 1. So this is basically minus j1 ohm, right? And then we have 1 Henry inductor, so that is j omega L, so that is j omega is 5 and L is 1, so that is j 5 ohm. So uh, let us now redraw this circuit again in the phasor domain. This 8 ohm resistance is unaffected whether it is in the time domain or in the phasor domain because the resistance is insensitive to frequency. So that is 30 angle 0 degrees volts. This is 8 ohm, and here we have minus j1 ohm and j 5 ohm, and this is voltage due to this source alone. This is now not V1, V0 is the total response due to both the sources. Let's call this V01, right? And let's call this Fig 3. So this circuit can be solved in many ways. We are interested in finding this voltage source across this capacitor. So the voltage across this capacitor is the same as the voltage across this inductor. So what we could do is we could find the equivalent impedance of both these branches, and then that equivalent impedance will be in series with this 8 ohm resistance, and we can use voltage divider rule to find the voltage V01 then. Or we can use the node analysis here. We can even use the mesh analysis, but the convenient will be the node analysis. Let's try node analysis. So let's call this is voltage V01 in the phasor domain, and this is the reference node. So the first equation uh, uh, is to be for this branch, and then the second equation for this branch, and the term, there will be one equation because there is one node only. The first term will be the current in this branch, then in this branch, and this in branch. So using KCL, uh, we can use any form of the KCL. But let's suppose here all the currents are leaving the node, sum of all the currents leaving the node is equal to 0. So the current leaving the node here can be found leaving the node this way, leaving the node this way, or leaving the node this way. So V01 minus 30, V01 minus 30, angle 0 means it has only real part, right? Imaginary part is 0. So V01 minus 30 divided by 8 plus V01 divided by minus J1 plus V01 divided by J5, right? The current through this, so V01 divided by J5, and V01 minus 0 divided by minus J1, and V01 minus 30 divided by 8. So these are the three currents, right? Voltage divided by the impedance, voltage divided by the impedance. So the sum of these currents is 0. So let's take the imaginary part in the denominator to the numerator. Whenever we have a complex number or imaginary number in the denominator, we need to rationalize that term and remove it from the denominator, right? So this is V01 minus 30 divided by 8, and this is minus j. So when j 1 over j is equal to minus j, so when j goes to the numerator, so it will be minus minus plus, so this will be plus j v01, and this will be minus j v01 divided by 5 is equal to 0. So we can multiply this whole equation by 40. So this will be this will leave a 5 here, so 5 V01 minus 150 plus J 40 V0 minus J V01, sorry, J minus J8 V01 is equal to 0. So 5 5 V01 plus J40 V01 minus J80, so that would be J32. So 5 plus J32 V01, right? And the constant term is taken on the right side, that is 150. So V01 is equal to 150 divided by 5 plus J32. So V01. So the complex number in the denominator is in rectangular form. It will be better if we transform this to the um, polar form, and then we perform the division. So 150 divided by, so let's transform this to polar, 5 J32. So that is basically 32.39, and the angle is 81.12 degrees. So V01 is equal to 150 divided by 32.39, and that is 4.63, right? And angle is minus 81.12 degrees volts. So this result is in the phasor domain. We need to transform this result back to the time domain. So V01 is equal to 4.63. So it is sine here, right? Remember, we transform directly from the sine to the phasor domain. So sine, and the angular frequency is 5t, and the phase is minus 81.12 degrees volts. So this is the first part of our result. So uh, as I told you earlier, we could have actually find the equivalent impedance here, parallel impedance, and then we can use the voltage divider rule to find the voltage V01. So let's try that method also. For example, so let Z1 denote the minus J1 parallel with J5, this parallel impedance, right? So Z1 is equal to minus J1 into J5. Z1 is equal to minus J1 into J5 divided by minus J1 plus J5, right? So the equivalent impedance Z1 is equal to uh, so j square is minus 1. So minus 1 multiplied by minus 1 here will be plus. So that will be 5 over uh, minus j1 plus j5. So that will be j 4, right? So we have z1 is equal to minus 5 over 4 j. When j goes up, it will give a minus here. So this is the equivalent impedance of the parallel combination. So the resulting circuit will be like this impedance here. Then this is Z1, this is 8 ohm, and this is our voltage source V here, right? Which is 30 angle 0 degrees. So we are interested to find this voltage Z1 and across Z1, and that is V01. So V01 using the voltage divider rule is given by uh, Z1 divided by Z1 plus 8 into this voltage V, which is 30 angle 0 degrees. So V01 is equal to minus 5 over 4 J divided by minus 5 over 4 J and plus 8, right? So again, we have a rectangular number in the denominator, and we need to perform a division. So we better off if we transform it into the polar form. So V01 is equal to minus 5 over 4 J divided by, let's transform this into the polar form. So uh, 8, real part is 8. So minus 5 over 4J. So that gives us 8.1 angle minus 8.88 degrees, right? So V01 is equal to Uh, so this minus 5 over 4 or 5 over 4 angle minus 90 degrees. We can minus 5 over 4 j can be written as 5 over 4 angle minus 90 degrees, right? So 5 divided by 4 and that divided by 8.1. And sorry, we also need to multiply by 30 angle 0 degrees here and 30 angle 0 degrees here, right? And multiplied by 30. So that gives us again 4.63, and the angle is minus 90 plus 8.88. So that gives us minus 81.12 degrees volts, which is the same result that we obtained here, right? So again we have V01 is equal to 4.63 sine 5t minus 81.12 degrees volts. So this is V01 is using the alternate method. So now we have found V01 due to this voltage source alone. We turned off the current source. What we will do now is we will turn off the voltage source and find the voltage across this capacitor due to the current source. So how do we turn off the voltage source? We short circuit the voltage source, right? For when we remove the current source, we open the source, but when we turn off the voltage source, we short circuit the source. So turn off voltage source, that is short circuit the source. So here is the new circuit diagram. Sorry, we need to short circuit it. So this is 8 ohm and this is the short circuit, right? And this here is the capacitor, this here is the inductor, and this here is the current source, and that is 2 cos 10t amperes. This is 1 Henry, this is 0.2 farad, and let the voltage due to this current source here be V02, right? And let's call this fig. This was fig 1, 2, 3, and let's call this fig 4. So this will be figure number 5. So uh, remember that we cannot use these parameters here, the transformed parameters, the phasor domain impedances, equivalent impedances in this circuit, because these impedances were found using this angular frequency omega is equal to 5. We need to recalculate the impedances for the inductor and the capacitor here using the revised angular frequency of this current source. The angular frequency now omega is equal to 10 radians per second, right? Omega is 10 radians per second, and so 0.2 farad capacitor will be 1 over j omega c. It will be minus j over omega is 10, and we have 0.2 here. So 10 multiplied by 0.2 is 2. So that is minus j over 2 or minus j 0.5 ohm, right? And for the 1 Henry inductor, we have J omega L, that is J. Omega is 10 and L is 1, so that is J 10 ohm, right? So, and this source here, uh, 2 cos 10t, so that will be transformed to 2 angle 0 degrees volts. So the transformed diagram in the phasor domain, revised diagram in the phasor domain, this is 8 ohm, right? And we have this impedance here, the capacitor, then this inductor, and then this current source. So this is J10 ohm now, this is minus J 0.5, and this is 2 angle 0 degrees amperes. Sorry, this is amperes, not volt here. So this is our figure number 6. Again, uh, we are interested to find voltage V02 here. Now, again, this circuit can be solved using many ways. For example, we can find the equivalent impedance of all these three branches, and then using this current, we can find the voltage. That is the equivalent impedance multiplied by this current will give us the voltage across all these three branches, which is the same. See the voltage here, this all these three impedances are in parallel. This is 8 ohm, this capacitor at minus J 0.5, and this inductor at J 10 ohm. All these three branches are in parallel. So voltage V02 here across the capacitor is the same as the voltage across the inductor, as the voltage across the resistance. So what we can do is we can find the equivalent impedance of these three branches, and the current flowing through, if we multiply the current flowing through that equivalent impedance, which is this source, so that will give us the voltage V02. Or we can use the nodal analysis, plain nodal analysis. So let's do the node analysis, and this is the voltage V02 here, and this is our reference point. So we need a single equation because we have a single node. The other is the reference node, and this equation will have four terms: one current flowing through this branch, and second here, third here, and fourth here. So the current, we say that current, all the sum of all the currents leaving the node is a zero. This is the Kirchhoff's current law that we will use here to find the nodal equation. So the current through this branch is V02. The voltage here is V02, right? Minus zero voltage here, right? And then divided by 8. So V02 minus 0, that over 8, plus V02 minus 0 divided by minus J 0.5, V02 divided by minus J over 2. So J over 2, J 0.5 is basically J over 2. So J over 2 takes 2 here, right? And then plus V02 divided by J10, right? And the current leaving the node is given by the minus 2 here, because this current, the direction of this current is in this way. So if we say that current leaving the node, we take the current opposite to the one given here. So this will be minus 2. We do not do any division here because the current is already given in this branch, this which is this source, right? So this is equal to 0. So again, what we'll need to do is we need to uh, uh, take the transform the imaginary numbers in the denominator and take them to the numerator. So V02 over 8, and this is minus j, and when j goes up it will be minus again, so minus minus plus, plus j 2 V02 and minus j V02 over 10, and we take the constant term on the right side, right? So this is uh, the modified form of this equation here, and we can multiply it throughout by 40, right? Uh, so 5 V02 plus J 40 into 2, 80 V02 minus uh, J 4 V02 is equal to 40 into 2 is 80, right? So this will leave us with 5 uh, V02 plus J 5 plus J 80 minus 4 is 76. 5 plus J 76 V02 is equal to 80. So V02 is equal to 80 divided by 5 plus J 76. So we again need to transform the number in the numerator to the polar form for the division. So 5 and J76. This gives us 76.16 angle 86.24 degrees, right? So V02 is equal to 80 divided by 76.16, that is 1.05, and angle is minus 86.24 degrees volts. So this is the voltage now due to the current source. So transforming this back to the time domain, so V02t is equal to 1.05, and we now use cosine function here to transform, because we use the cosine as the base here. So cos angular frequency is 10t minus 86.24 degrees volts. So this is the voltage across this capacitor due to the current source. So we need to add the both the voltages here, V01 and V02, to find the total response. So V0t, that's the total response due to both these sources, V01 plus V02. So V naught T is given by V1 was 4.63 sine 5t minus 81.12 and plus 1.05 cos 10t minus 86.24 degrees volts. So this is the voltage here, V naught, due to both these sources operating at different frequencies.